Well, currently, what I'm doing now, which I find quite interesting, is, and have for the last 12 or 13 years, myself and a couple of other local practitioners teach the HVAC course at the University of Arizona in the Aerospace Mechanical Engineering Department. And it's always interesting to watch young, energetic students come up and go through this and how they have, they've been in school for 4 or 5 years, and how they have not much of a perspective on HVACs. So many people think because what we do happens above the ceiling and below the floor and in the walls. It doesn't, we're not very
Yeah.
noticeable.
It's not a touchy-feely thing.
No, and if it does make noise, then we call somebody to fix that because it's not supposed to make noise. But the students have changed a little bit over the years, certainly changed since I was there in the 70s. And what probably shocks we'll have as few as 12 students and as many as, I think one year we had 48 students.
Wow.
in our class. After their 4 or 5 years in undergraduate school at the U of A, this is their first real course taught by practitioners. And Peter DeMars is the lead guy who does all the heavy lifting. But we make it clear in the first 2 or 3 lectures of the new semester with this class that, we're professionals, we're the ones that are out there working, getting the job done, and you've spent 4 years learning the theory behind things, and you could go through a lot of engineering courses, and when you get to the exams and those other exercises, a lot of the instructors or professors will say, well, you got everything right, you got the process right, but you forgot to invert it or something. Well, you forget that, you get 0. That professor might give you 50% credit because you got the theory right. Well, if the answer's wrong, you get 0. Because in our business, we get paid to get the right answer. The structural guy can't let the building fall down. We can't let the HVAC systems fail. So from our perspective, we hold the students, I don't want to say to a higher level, I'm just saying that you've got to get the answer right. At least in the ballpark. And we also begin to instruct our students, which is a little odd for most of them, because when you first start to teach them how to do load calculations and they start submitting things, they got, in this room the load was 22,862.4 BTUs an hour. So then you got to go back and say, no, in the HVAC world, all we need are 3 significant figures. And you remind them that in 1969, NASA went to the moon and back on 3 significant figures. So we don't really need that. All we really need to know is that the load in this room is 11,200 BTUs an hour. Why do we need 5 more digits after that? We can't buy the equipment that way.
Yep.
It's not like, well, I need a 118.2 ton air-cooled chiller. No. Depending upon how you rate this thing, you're going to buy a 130 ton air-cooled chiller. And it is, and sometimes it takes darn near the whole semester to keep the students from, again, just carrying because they can't. Everything is done in Excel, we teach them, okay, let me show you this little part of Excel. This is the rounding function. This is what you need to use every time you submit an answer to us. And here's how you set up and you can round off the answer. And we need to do that because we tell them, you do that and you're implying a level of accuracy that doesn't exist. I says, when you go to calculate the heat transfer through that sunlit wall right there on the south side of this building at 1 o'clock on a June day, how long does it take for that? What's the color of that thing? What's it made out of? How long will it take for that energy to get through here? How much of it's radiation, how much of it's conduction? And you can't get that degree of accuracy. So please, just, your U factors are, 2 significant figures, like 0.08, okay, or 0.09 or 0.1, but don't be going that my U factor's .10046. I mean, well, that makes no sense. So we continue to do that, but they do struggle with that. So the students also have a difficult time when we get into the system side of things, and we go through our load calculations, and then we start our equipment selection, and we spend a lot of time on psychrometrics, which I think is really important for the students to understand. And they pretty much pick up within the first 2 weeks that we're going to be handling the psychrometric chart a lot. Everything we do has to be portrayed on that psychrometric chart, and we share a lot of different things. In fact, I brought a couple that have, I don't know how well we're going to be able to see this, but this is something that GLHN's been doing for over 40 years. We take a standard psychrometric chart, and then we'll go on here, and we'll go up here at a 78 degree dry bulb and a 65 degree wet bulb, and that causes 4 quadrants: quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So we've segmented, and that's what we call this, a segmented psychrometric chart. And then we go in and we go over the last 10 years, 15 years of weather data for that location. This happens to be Tucson. And we figure out how many hours is the outside air temperature below 78 but above a 65 degree wet bulb. And we categorize those, and we do that. And how many hours is the outside air temperature, again, below 78 degrees dry bulb, but also below a 65. And then consequently, this is above and this is above, and you can see just how that works. And it's important for the students to understand how the ambient air conditions affect their system, because every commercial HVAC system brings in a dedicated amount of outside air that has to be filtered, cooled, and then sent out into the building. So it's important to know where that outside air is. And just as a thought here in Tucson, if you then go back and look, and what we would do is for each city we would plot a typical May or June day. Down here we'd come up with saying, okay, let's take all the weather data for the last 30 years. Let's go into May and June, and let's see what the average dry bulb and wet bulb is at 6 o'clock in the morning, at 9 o'clock in the morning, at noon, at 3, 4, and 6 o'clock at night, and then back. So we had a diurnal plot of where that's at. Well, interestingly, you can't quite see it here because the dew point line overshadows it, but in May and June in Tucson, Arizona, historically, I mean over almost 50 years of weather data, we lie along almost a constant dew point. The dew point at 3 o'clock in the morning is the same dew point as it is in the afternoon. It's probably something like 40 degrees. Whereas when we shift up to July and August, now this little plot is the standard July or August day. And you can see now, one, it's moved way up. We're above a 55 degree dew point. But what's more noticeable is it lies almost, that diurnal plot lies almost along a constant wet bulb line. I offer no understanding of why here it's along a constant dew point line and here it's more along a constant wet bulb line. It's just the way that Tucson is. And this in itself is kind of interesting. You can spend a lot of time thinking about this and talking about it, but it's mainly brought home when we show the students that, oh, by the way, here's another one done exactly the same way, but this is for Miami, Florida. Now, you don't see anything down here in Miami, Florida. They've never seen a 30 degree dew point in Miami, Florida. Here's their typical May or June day and their typical July or August day. I mean, they're way, way up here. So, if I was looking at where do I want to relocate to, if you've been living in this world, you really don't probably want to go to this world, okay? But it is interesting because we have these plots and we show them to the students for Tucson, Phoenix, which isn't much different. Then El Paso, that's close to Tucson, kind of. Then we'll go over to San Diego. My God, those people. Yeah, Yeah, it's a good thing that Tucson looks like this, or would have 4 million Californians moving in, okay? We will let San Diego have their pleasures, and we'll keep ours, okay?
There you go.
We'll keep our house prices below $300,000 or whatever. So it is and the students begin to understand this. And we're always pleased that there's usually 3 or 4 of the students that are looking for summer internships. And I'll talk to the guys over at GLHN and say, hey, have we got some internships available? And we'll usually point out who we think are the more energetic, committed students to this. So I think that's been an interesting part of what I've been doing now for the last 12 or 13 years, and I kind of enjoy that.
So, well, what's probably the biggest piece of advice that you can give to them, as they have to come out into the real world? I'd like to know what you think, because I know what I think.
Yeah, I guess we talk to the students regardless of what profession they're going to go in. I mean, if you're getting a degree in mechanical engineering, then obviously you would like to do that. And typically most graduating mechanical engineers go to work for what we call one of the generals, General Electric, General Dynamics, General Motors, and only probably about 5% ever drift over into the HVAC or the built environment. We tend to say, hey, if you're really interested in building things, okay? Because to me, that's the most fun about this. I mean, as I've said many times, I look at my whole 50-year career in this as just a great hobby that I got well paid for. I mean, it's really amazing how much fun this is to start a new project, and someone else was using somebody else's money, a lot of times
Yep.
the University of Arizona, and you've been wondering about how would two-stage evap cooling work in this, or could I add this to that? And you then just say, oh, well, because nobody's telling you much other than they just want it to work and have the energy levels right. So you can do not just whatever you want, but you've got a lot of freedom. You've got a lot of freedom to pick the system that you want and make it work. And then what's really great is you get done with all these drawings, all these calculations, put all this together, send it out, and a contractor gets selected. And then you get to go out there, when they're hanging sheet metal and doing all of this, you get to wander around it. And of course you get to hear what the contractor, contractors don't say some good things about engineers occasionally, but you got to learn to accept that. And if you think you're perfect, you're not. You're not. You're going to make mistakes. It's how you come back from those mistakes that's so important. And the biggest single thing about being an engineer is integrity and honesty. I mean, one of the things we talk about is most engineers, especially if you go to work for General Motors, General Electric, General Dynamics, you'll end up being in a leadership position. Maybe as little as 5 or 6 years out of college, because when they look around who they're going to promote to vice president, they got as much damn engineers. So typically engineers get promoted up. And what you have to do is remember that the very essence of leadership is honesty, integrity, and vision. You've got to, as the leader, you've got to help develop the collective vision of your group, and then make sure you constantly articulate that vision and that the group is moving forward. And I know one of the examples we give the students is that the Challenger that in 1983 crashed, okay? And what that was a bunch of darn engineers that were running all of that stuff, and then NASA had promoted all these engineers to senior directors, and then when it came time to launch that, the other engineers weren't strong enough to stand up and say, no, we're not going to launch today. It's not safe. But they didn't. And 7 people died because of that. So what engineers have to remember is you have a responsibility to stand up, and when things aren't right, you got to stand up and tell these people that, nope, best we don't do that, So that's one of our parting suggestions. to the young engineers, is honesty, integrity, and sometimes you gotta speak, truth to power, and you gotta do it, because as an engineer, that's part of your obligation.
Whether people want to hear it or not,
Whether people wanna hear it or not.
you got to say it
You gotta say it, because.
and stand
if
your
you-
ground.
And stand your ground, because if you don't, nobody, as we have all seen, very recently, politicians sometimes can't tell what's right or wrong, but the engineer has to at least stand up, and sometimes you gotta walk away and just say, okay, I'm done. I'm done. This is important enough that, because we're guided by physics, thermodynamics, fluid dynamics, and all we can state is, yeah, this is what you do this, and then this could happen.